Yeah.
Mm. So, hello everyone, welcome to the first SPARKS seminars for this semester. And this time we're glad to invite Fatme. She's from UIC and she's going to present her research. And let me get some introduction for her. Fatme is a PhD student in the Electrical Computer Engineering Department at the University of Illinois at Chicago. And she's under the supervision of Professor Hoya Saproglu. And she received her Bachelor of Science degree in the Electrical Engineering department from the University of Tehran in 2022. And her research focused on private and secure distributed machine learning. So I'll open the floor to you, Fatme, and let you introduce your work.
Thank you very much for your kind introduction. Okay, so let me share my screen. Here's okay, can you see my screen now?
Yes.
Oh. Okay, so hi everyone, I'm Fatima, and today I'm going to present our work on privacy-preserving hierarchical model distributed inference. This is a joint work with Dr. Keshkar Jahrami from Seagate Technology and Professor Safar Group. Okay, so machine learning has become a powerful tool for supporting many applications, such as mobile healthcare, self-driven cars, agriculture, marketing, etc. These applications generate vast amounts of data at the edge, requiring swift processing for timely responses. On the other hand, ML models are getting larger and more complex, so they require higher computation, storage, and memory, which are usually constrained in the edge, but abundant in the cloud. So the typical scenario is that the data owner in the edge is geographically separated from the model owner in the cloud. The geographically separated nature of the data and model owners poses challenges for ML inference as a service. We can naturally use the client-server approach where the client sends its data to the model owner in the cloud server to get the ML inference results. But this approach violates data privacy and also incurs high communication overhead between the model owners and the data owners, which is usually the bottleneck in today's systems. Very promising privacy-preserving approaches have been investigated in the literature, but still suffer from high communication costs between the data and model owners. And such high communication costs between the data and model owners undermines the effectiveness of ML inference applications that require less latency and real-time responses. Very promising solution is hierarchical setup where we have clients which own or generate data, a cloud server that owns a pre-trained ML model, and edge servers or compute nodes that will perform ML inference. This approach advocates that the edge servers perform ML inference by preserving the privacy of data from the client's perspective and ML model from the cloud server's perspective. And the hierarchical ML inference promises to reduce the communication overhead between the client and the cloud server by confining the communication cost between the client and edge servers, noting that the client and edge servers can communicate through a high-speed edge link as they are geographically close. Despite this promise, the potential of hierarchical ML inference has not yet been fully explored in terms of utilizing available resources in the edge servers. So in this work, we focus on reducing the amount of communication to or from the cloud server while preserving the privacy of both data and ML model. And also our work employs model distributed inference or model parallelization at the edge servers to speed up ML inference. But what is model distributed inference? Model distributed inference is emerging as a promising solution where ML model is distributed across edge servers. So how does it work? First, the client has to send its data to an edge server, and then the edge server, after receiving the data, processes the layers assigned to it and generates a feature vector that is the output of those assigned layers and send it to the next edge server. Each edge server, after receiving a feature vector, processes the layers assigned to it. And then finally, the last edge server that is processing the last few layers of the ML model sends the output of the ML inference to the client. So in this approach, the edge servers are computing the ML inference by using model parallelization and data pipelining, so ML inference becomes faster. But the crucial question of how to provide privacy to both data and ML model should be addressed, which is the focus of this work, private MDI. More formally, we consider the problem of computing the ML inference result of the client's input data X using an ML model M and give the output M of X in a privacy preserving manner. We assume that the ML model consists of capital L layers. At a high level, our solution uses additive secret sharing, linear homomorphic encryption for linear operations and exchanging the keys. And we use garbled secret and three-party oblivious transfer for nonlinear operations. We also divide the protocol into offline and online phases and to reduce the online phase latency. And I would like to note that the offline phase is independent of the input data X. So now let's go over the system model. Our setup consists of three main components: a cloud server that we call the model owner, a client that we call the data owner, and edge servers or compute nodes that perform ML inference. The edge servers are divided into clusters, where each cluster consists of T+2 edge servers, 12 feature, Grobler, and evaluator servers. For our threat model, we assume that all the participants are semi-honest, meaning that they follow the protocol, but they are curious. And within each cluster, up to T out of T+2 edge servers may collude to obtain data. Lastly, in terms of model distribution, we account for the fact that different clusters of edge servers may have different and time-varying computational capacities. Thus, a cluster with higher computing power should process more layers than the others. And we do this based on the previous work of our group, ARNDI. So now let's go over the details of the private NDI operation. As I mentioned earlier, we divide the protocol into offline and online phases. The offline phase is responsible to handle computationally intensive tasks in advance, enabling faster execution of the online computation. Additionally, the offline phase reduces the communication between the cloud server and the client, which is a bottleneck link in the online phase. So in the offline phase, to start the protocol, first the client generates a set of public key and secret keys using a key generation algorithm. And also it generates a random sample R1. And then the client uses the public key that it generated and the R1 sample and encrypt the R1 sample homomorphically and sends it to the cloud server. So during this presentation, when a variable has the superscript encrypted, it means that it's homomorphically encrypted. Then the cloud server initializes C1 encrypted as R1 encrypted. Then for each layer L, the cloud server generates a random sample as L and creates secret shares of the model parameters ML and the random sample as L using additive secret sharing. Then the cloud server sends the MLV and SLV shares to the corresponding computing edge server V of each cluster. And these shares will later be used in the online phase by the edge servers to compute and process the layers assigned to them in a privacy preserving manner. Next, the cloud server computes the encryption of the model parameters ML and the random sample SL using the linear homomorphic encryption algorithm, and also computes this term, ML encrypted multiplied by CL encrypted plus SL encrypted. Now it's time for the model owner to determine the values of CL+1 encrypted. These values are later used in the online phase. They do this based on the linearity of the layer. So if layer L has only linear equations, the cloud server will set CL+1 encrypted to the term that is computed in a previous step. Otherwise, that is, if layer L has also nonlinear operations, nonlinear activation functions, it will first send the computed term to the client. And later, in the next step, the client will generate a new random sample RL+1, and then again encrypt it with the public key and then send it to the cloud server. So now the cloud server sets CL+1 encrypted to RL+1 encrypted. Now CL encrypted is also added to the parameters of the cloud server. And the previous steps are all repeated for each layer L from 1 to capital L. And in the last layer, the cloud server sends the ciphertext C capital L+1 encrypted to the client. And because the client has the secret key, so it can decrypt this value and gets C capital L+1. And it will later use this value in the online phase to decrypt the inference result that is received from the last cluster. So now all the key and parameter exchanges are done, but we have one more operation left in the offline phase. And that is, how do we pre-process for the nonlinear operations? So if layer L has nonlinear operations, we use a garbage circuit to compute the nonlinear activation functions. For this purpose, each cluster has a garbler and validator server. The garbler server first generates a garbage circuit denoted as C tilde, which encodes the nonlinear activation function as a Boolean circuit, and then sends this garbage circuit to the evaluator server. Additionally, the garbler and evaluator and the client communicate through a three-party oblivious transfer protocol to exchange the corresponding labels of the inputs of the two inputs out of the three inputs of the garbage circuit. So at the end of this protocol, the evaluator server receives the labels corresponding to these two inputs, MLCL plus SL and RL+1, which are both known by the client. So we talked about RL+1, which the client generated in the previous steps, and also MLCL plus SL was the term that it received in the encrypted format from the cloud server. And because the client has a secret key, so it can decrypt it and gets the plain text. And to make this work, we designed a novel three-party oblivious transfer protocol. So our novel three-party oblivious transfer protocol is inspired by ProxyOT, but our protocol provides information theoretic privacy, whereas ProxyOT is cryptographic. The main components of our protocol are the client, garbler server, and validator server. The client has a 1-bit input I, and the garbler server has the two input labels K0 and K1. And also the client and the evaluator server will later generate a 1-bit random sample B using a pseudo-random generator function with the same seed, and the evaluator server and the garbler server will also generate U0 and U1 similarly. One more thing to note is that UJ and KJ are both binary strings of length kappa, where kappa is the security parameter. So the goal of this algorithm, this protocol, is for the evaluator server to get KI. So without knowing, so if I is 0 or 1, if it's 0, evaluator server will get K0 without knowing any other information about K1, and without also knowing that if this is K0 or K1. So how does the protocol work? First, the client masks its input I and send it to the garbler server. Then the garbler server will mask the two labels that it has and send it to the client. Now the client chooses one of these messages according to I. So if it's I, it will I is equal to 0. It will choose the first one, and then send that chosen message, which is like ki XORed by UB, to the evaluator server. Now the evaluator server, knowing U0, U1, and B, so it knows UB, can decrypt this value and get ki. At the end of the offline operation, each node in the system has all the necessary parameters required for privacy-preserving computation during the online phase. So now we move on to the online operation. The online phase of private NDI is responsible for computing the ML inference function, M of X, given the client input data X. And also, because there is no communication between the cloud server and the edge servers or the client, I removed the cloud server from this picture. So to start the online phase, first the client masks its input X and send it to the garbler server of the first cluster. The message that it sent is X1 minus C1, which X1 is set to X and C1 is set to R1, which we know that it was a random sample generated in the offline phase, and X is the actual input data. Then each layer L assigned to cluster J is processed with input XL minus CL, where XL is the result of the previous L minus 1 layers of the ML model, and CL is the decrypted value of CL encrypted, which we determined in the offline operation. And yeah, so let's go over to the details of how each cluster performed the computation. So they handle computations based on whether the layer has linear or nonlinear operations. So if layer L has only linear operations, first the garbler server of that cluster will send the input of the caret layer, which is XL minus CL, to the other T computing edge servers. So now each computing edge server, knowing the shares of MLB and SLB, which they obtained in the offline phase, and the input of the layer, which is XL minus CL. So they will compute a share of ML multiplied by XL minus CL minus SL. Now, in the next step, the garbler server aggregates all the results from other computing edge servers and adds its own share and determines ML multiplied by XL minus CL minus SL. And note that the other T computing edge servers protect their share from the garbler server by adding their own share of SL parameter, which is a random sample. So it's private. And so if layer L has only linear components, so that would be, this term would be the input of the next layer, denoted as XL plus 1 minus RL plus 1. Otherwise, if layer L has also nonlinear components, so first the garbler server has to send the labels corresponding to the third input of the garbled circuit to the evaluator. So now the garbler server, after sending the labels corresponding to this term to the evaluator server, knowing the three labels and the garbled circuit, can evaluate the circuit and outputs C of ML multiplied by XL minus RL plus 1, and send it to the next cluster's garbler. Finally, the last cluster calculates and sends X capital L plus 1 minus C capital L plus 1 to the client. So the client can obtain X capital L plus 1 by knowing C capital L plus 1, which was one of the steps that we did in the offline operation. So it knows C capital L plus 1, and it can get the M of X, which is the ML inference result. And that finishes the operation of private NDI's protocol. So now, to give you a better understanding of how private MDI protocols functionality works, so I will now walk you through a demo. In this demonstration, we are considering a minion model on a CPR10 dataset using 120 data samples. And one more thing to note is that, as I mentioned earlier, so we divide the protocol into offline and online phases. So we will start with offline operation here. And as you can see here, the R11 encrypted. So during the demo, you can see we have two subindices. The first one denotes the number of layer that is being processed. So this minimal model has like 8 layers. So this value will change from 1 to 8. And the second subindex shows the number of in the offline phase, it shows the number of the pre-processing point that is being processed, and in the online phase, it shows the data point number that is being processed. So let's start the demo. So the offline operation starts first with the client sending its random sample to the cloud server, and then the cloud server multiplying with its model parameter and adding another random sample to it and send it back to the client. So this will has to be done for each of the layers and each pre-processing point separately. So it will go all the way to 120 and for all the layers, 8 layers. And the next step in the offline operation is for the cloud server to share the signatures of the model parameters and the random sample. So we will share the model parameters only once because they do not change. But in order to protect privacy, we have to share the random samples separately for each layer and for each pre-processing point. Yeah, so this will continue until the last point. And then we move on to the online operation, which starts by the client sending its data to the first cluster. And after some point, we can see that because we are using data pipelining, after some time, all the clusters are processing at the same time. This shows how model parallelization and data pipelining can reduce the inference latency. So it will go all the way. And in the last step, the last cluster will send the inference result in the encrypted format back to the client. Okay, so for the privacy guarantee, we consider common correctness and security requirements as summarized here. We prove that private MDI is secure based on the conditions outlined in this definition using garbled circuit, linear homomorphic encryption, additive secret sharing, and three-party OT, oblivious transfer. Now let's go over the communication overhead comparison of private NDI and the baselines. So you can, in the online phase. So you can see here, compared to Delphi in the first column, the private NDI improves by moving the costly communication between the cloud server and the client to the edge servers. Compared to a secure NN, private NDI outperforms by reducing the linear communication overhead. And also we have Falcon here, but only Falcon has better communication overhead than private MDI, but they're limited in the sense that they do not support collusion among the edge servers because they're using replicated secret sharing. And they also incur higher computation overhead in the linear part. And they also do not consider model distributed inference. And one more thing is that for their nonlinearity, because they have like specific nonlinearity, nonlinear algorithms in a privacy preserving manner, so they do not support all of the nonlinear activation functions. We also implemented and evaluated private NDI across various architectures and datasets. We use a desktop computer as the cloud server and different instances of JetStream 2 from NSF Access Computing Platform as the edge servers and the client. One more thing to note here is that the specifications of the each cluster are provided in the table. And as you can see here, the primary clusters have higher computational capacity because initial layers of the ML model have greater number of parameters. So they incur more computational load. And one more thing is that the devices are connected via TCP. So here we have the experimental results of private NDI compared to Delphi for Minion model and CPAR10 dataset. This is the similar architecture and dataset to the demo that we saw earlier. So in both figures, in the offline and online phases, the x-axis shows the number of clusters from 1 to 8, and the y-axis shows the inference time in seconds per image. And as you can see, private NDI in both figures is outperforming Delphi with greater performance in online phase as the number of clusters increases. And you see that's because when we increase the number of cluster, so we divide the model layers into more clusters. So initially, we are reducing the latency in that sense. Similar to the previous slide here, we have the evaluation of private NDI's performance compared to Delphi, but here we are using a ResNet32 model and CPAR100 dataset. Again, in both figures, and the x-axis shows the number of clusters from 1 to 8, and the y-axis shows the inference time in seconds per image. And as you can see in the online phase, so we can see the greater performance of the private NDI as the number of clusters increases, and that shows how our approach is scalable and efficient in terms of increasing of number of clusters. Here we have another set of evaluations, the inference delay in the online phase compared to Falcon and SecureNet across Minion and MNIST dataset, AlexNet and Tiny ImageNet dataset, and BGG16 and Tiny ImageNet dataset. So you can see here, compared to like Falcon, at the like for Minion and MNIST, we do not outperform Falcon. We have improvement in AlexNet, and then we outperform in BGG16. The takeaway from this table is that as the ML model gets larger and more complex, our approach signifies better because and now in the larger ML models, the computation is becoming the bottleneck, not the communication. As the computation is becoming the bottleneck because we are using model distributed inference and model parallelization with data pipelining, so we reduce the overall latency. To summarize, in this paper, we designed a privacy-preserving hierarchical model distributed inference, private NDI protocol, to speed up ML inference in a hierarchical setup while providing privacy to both data and ML model. And our approach uses model distributed inference at the edge servers, reduces the amount of communication to or from the cloud server to reduce ML inference time, and uses additive secret sharing with homomorphic encryption to reduce the number of computations. And with the experimental results, we demonstrated that private NDI significantly reduces the ML inference time as compared to the baselines. Thank you very much. And if you have any questions, I would be happy to answer.
So first of all, thank you, Fatima, for your wonderful talk. It's very interesting to see this privacy-preserving machine learning inference algorithm. Yeah, I'll open. So is there any question for the talk from the audience? Just go ahead and mute yourself and ask questions if you. So I can open the floor. I'm trying to understand your figure, actually your figure better. So in your figure for the offline phase, I'm just curious to see the number of communication almost stays the same when you increase the clusters. Could you explain more on this? Because from my understanding, if you increase the number of clusters, right, and you might need more computation in between these clusters. So I'm just curious why it almost stays the same here.
Oh, okay. Yeah, very, very good question. So if I go back to the demo, maybe. So here, the point is that because in the offline operation we are not doing any parallelization. So when we increase the number of clusters, it's just it brings the benefits for just the online phase. So because and like there is no communication between the clusters in the offline operation, so that's another reason. The main communication in the offline phase is when the cloud server and the client communicate with each other for this first part to compute the part of the linear part that they use in the online phase. And also the other main communication is when the cloud server is sending the data, the signatures of the random sample and the model parameters to each of the cluster. So because we are dividing the layers, so the overall number of communication that we have is a constant number, and then we increase the number of clusters. It has just different different messages have to be sent to different number of clusters, but the overall communication is just the same.
I see. Okay. Yeah, thank you for explanation.
Yeah, you're welcome.
Any other questions from the audience?
Hi, I can ask a question.
Hey.
So, how do you decide which parts of the model are executed at the cloud versus its servers?
So we do not we do not the cloud server doesn't, so as you can see in the online operation, we have no cloud server. So the cloud server doesn't participate in the online operation, and that's how we reduce the online inference latency, and we just divide the model across these computing edge servers. So the cloud server doesn't participate in this. And if your question is like how do we, okay, let me go to here. Yeah, here is the offline phase, online phase. And if your question is how do we distribute the layers, like how many layers each cluster should process, or which layers each cluster should be processing, we do this based on it's like another paper of our group. So it somehow solves an optimization problem based on the computational resources of each cluster that it has, and then the bandwidth, and also the number of parameters that each layer has. So it's like a whole other problem.
Okay, yeah, thanks for the answer.
You're welcome.
So other questions? If there's no other questions, let's thank Fatma again for her wonderful talk, and thank you all for attending the SPARKS seminar today.
Thank you so much for having me.
Thank you for talking.
Thank you.